The following theorem says that if we apply a continuous function to the terms of a convergent sequence, the result is also convergent. The proof is left as exercise 88. Theorem 7. If the limit as n approaches infinity of a sub n equals big L, and the function f is continuous at big L, then the limit as n approaches infinity of f of a sub n equals f of big L. Example 9. Find the limit as n approaches infinity of sine of pi over n. Solution. Because the sine function is continuous at 0, theorem 7 enables us to write the limit as n approaches infinity of sine of pi over n equals sine of the limit as n approaches infinity of pi over n. So sine 0 equals 0. Example 10 discusses the convergence of the sequence a sub n equals n factorial over n to the power n, where n factorial equals 1 times 2 times 3 continued to n. Solution. Both numerator and denominator approach infinity as n approaches infinity, but here we have no corresponding function for use with L'Hospital's rule. X x factorial is not defined when x is not an integer. Let's write out a few terms to get a feeling for what happens to a sub n as n gets large. A sub 1 equals 1. A sub 2 equals 1 times 2 over 2 times 2. A sub 3 equals 1 times 2 times 3 over 3 cubed, or 3 times 3 times 3. And a sub n equals 1 times 2 times 3 times all the way to n over n times n, essentially n to the nth power. From my observation, it appears from these expressions and the graph in figure 10 that the terms are decreasing and perhaps approach 0. To confirm this, observe from equation 8 that a sub n equals 1 over n times open 2 times 3 all the way to the power n over n times n to continue to n close. Notice that the expression in parentheses is at most 1 because the numerator is less than or equal to the denominator. So a sub n is a sub n is greater than 0, but less than or equal to 1 over n. We know that 1 over n approaches 0 as n approaches infinity. Therefore, a sub n approaches 0 as n approaches infinity by the squeeze theorem. Off to the side, there's a sidebar that says creating graph sequences. Some computer algebra systems have special commands that enable us to create sequences and graph them directly. With most graphing calculators, however, sequences can be graphed by using parametric equations. For instance, the sequence in example 10 can be graphed by entering the parametric equations x equals t, y equals t factorial over t to the power t, and graphing in dot mode starting with t equals 1 and setting the t step equal to 1. The result is shown in figure 10. Figure 10.